Okay. Hi, everybody. Mrs. Pesic here. I am live with about half of Block 7. You want to give a shout out, Block 7? Okay. That's all they can do. And so we are looking at Section 3.1, and we're starting our conversation today about the nuclear power plant accident in Chernobyl in 1986 in what was then the Soviet Union. And we started off by looking at some pictures. Obviously, there's radiation there. And the town is like a ghost town. It had to be evacuated after this accident 32 years ago. And things are falling apart. This is the control room where there was a fatal series of errors during a safety test that triggered that meltdown. There's workers in plastic suits and respirators, and they can only work for like 15 minutes a day because of all the radiation. And a lot of children were born with defects, birth defects, and adults and children have thyroid problems and so on. So we are now looking at page 225 in your book on Chernobyl. So you would probably be well advised to take a look at that also. And we are typing in the equation that they gave us, which was, what is it, 10 times 1/2 parentheses control divided by. We decided that this was going to be an exponential decay because the base is 1/2. And I'm raising this to the x, not t, right? Over, was it 24,100? Okay, I'm not seeing anything. I think I'd better adjust my viewing window. Let's go menu, window zoom, window settings. And the x, they told us to graph it from 1986 and go out 100,000 years, correct? And 1986 is represented by 0. So I'm going to go 0 to 100,000. My y minimum, I would say, is 0, and my y maximum, how much are they saying? How many pounds was released? 10 pounds. So let's go from 0 to 10 pounds. Okay. And I say okay, and this is my graph. Are we okay with this? All right. So if we have this graph, and we want to know how much was left in, let's say, in 2018. We said this is 32 years later, right? So in 2018, I would plug in what number? Oh, I got to go menu, trace, graph trace, right? Menu, trace, graph trace. And if I want to know how much is left of the 10 pounds in 2018, I'm going to type in what number? 32. So I'm going to type in 32. And so how many pounds are left over? 9.99. So 32 years later, practically the same as it was when the accident happened, right? Because there's still 9.99 pounds out of the original 10 pounds. That's like nothing, right? Like practically it's all still there in the atmosphere. All right, what about in 100,000 years? So if I type in 100,000, so in 100,000 years, we'll be down to how much radiation or how many pounds of this substance? 0.5. So in 100,000 years, it'll be down to like 1/2 pound. Will it ever get down to 0 pounds? Probably not. Or definitely not. I don't know. I mean, this is a graph that's approaching a what? What do we call this power line? Horizontal asymptote. So the further out we go, is it ever going to cross that asymptote? No. It's never going to reach it. And so that means it's never going to be down to 0, right? Even if you go millions and millions of years out into the future. All right. So that's why people can't go back now 32 years later, because there's still, there's still most of the radiation. If not, just consider it like all the radiation is still there pretty much. Okay. All right. So that's this example. And then I think in your notes, we have another example here. Let Q, is this on your gift? Let Q represent the mass of radium. This particular radium is a 226Ra, whose half-life is 1,620 years. Oh, by the way, let's go back to our graph for a minute. What's the half-life for this particular plutonium that they're talking about at Chernobyl? What will be the half-life? In other words, have you heard of half-life before?
No.
Half-life, no, this is something different than a video game. Half-life in this context would be how many years out do you have to go for there to be half as much left as what you started with, right? So how many years out? So in other words, if I go 1,000 years out, well, I'm still at 9.72. What if I go 10,000 years out? Well, now I'm at 7.5. I'm still not to the half-life period, right? What happens if I try 20,000? I'm getting closer. Do you see how I'm gauging this by 5.63? Right, that's almost half of what we started with. As it turns out, I would have to plug in this number right here, this 24,100, because if I take x to be 24,100, 24,100 over 24,100 is equal to 1, right? And then I'll have 1/2 to the first, which is 1/2, and then 1/2 times 10 is 5. Does that make sense? So if I try 24,100, I get right to 5 pounds. So how many years would I have to go out past that? So I'm down to 2.5 grams or pounds, whatever units we're measuring. Add 12,050 to 24,100.
I think it's about 24,100.
24,100 plus 1250, like that. So that's 25,350. So.
I think he wants another 0.
Oh, yeah.
Oh, you want another 0 here? Oh, it doesn't let me do that. Let's see.
Yeah, 12,050.
Enter, come on. So you want another 0 here. So you want 36,600. 36.
Oh, yeah. That's before the 5.
What? Oh, 050, like curses. See, I'm not cursing. I'm being recorded, so I'm not cursing. I'm not even saying Jiminy Crickets. All right, 050. Like this?
Yeah.
36150. All right, so we're trying to see if 36150 is going to get us to what, 2.5?
I think it's,
Spencer,
I think it's 48,000.
where are you getting 48,200 from?
Because if the half-life is 24,000 for the element, it doesn't matter the amount. So if the amount's 5, and the half-life for that, it's the same number.
All right, does that make sense? That reasoning? So let's check that out. Sure enough, that gets us down to 2.5. So every time you go another 24,100 years in the future, you will have half left of what you started with. Does that make sense? So if I want to get down to 1.25, I would add on another 24,100 years and so on. Okay, back to our example here, which was about radium. And the formula we're using is 16 times 1/2 to the T over 1620. And it says determine the initial quantity when T equals 0. Determine the initial quantity when T equals 0. So if T is equal to 0, what do I get? 16 times 1/2 to the 0. 1/2 to the 0 is just 1, right? So I'm just going to get 16. So the initial quantity is 16. And we're supposed to sketch the graph over the interval T equals 0 to 5,000. So let's do this on our calculator. Adding a new graphs page. And this is 16 times, parentheses, raised to the, what is it? X over 1620. Okay, again, we're going to need to play around with our window. Menu, window zoom, window settings. So we want 0 to, what do they suggest? 5,000 years. And Y minimum is going to be 0. What's Y max going to be? 16. Because we're starting with 16. It's only going to go down from there. All right. And so I get this graph. Do you have a graph that looks like this? Okay. And at this point, you can take your graph and answer the follow-up questions like how much will remain after 1,000 years. We can go menu, trace, graph trace, and type in 1,000, right? And I'm getting 10.4. Does this make sense? Okay. All right, so, and it's perfect timing because that's where we're going to end this lesson. So thanks for watching.